Introduction to continuity. Goals here, understand the definition of continuity. We're going to see that limits play a role. That's why it's following after the limit stuff that we've done. Be able to find intervals where functions are continuous. And really what we're going to see here is basically find the domain, that's where it's continuous. And then be able to use continuity to find limits of composite functions. So composite functions, you've got that inside, you got the outside function. And we're going to see how continuity can help us just find the limits of those by focusing on the inner piece first. And then understand the Intermediate Value Theorem. So really useful for finding roots of functions or showing that roots exist in a certain interval. So the continuity definition, basically the concept of continuity says that the function's graph can be drawn without lifting your pencil from the paper. That's, maybe the layman way to think about it, but it works. If you can lift your pencil, then it's not continuous at that point. If you don't lift your pencil, then it's continuous. So that is, there's going to be no breaks in the graph as you draw it. So for example, this graph of f of x here, didn't have to lift the pencil at all, or my screen pen at all to draw it, and f of x then is continuous. So in general then, the definition of continuity at a point relies on the fact that the function value must be equal to the limit value at that point. So that is, the limit as x goes to a of f of x has to equal the f of a. And if you look up here at this graph, if I were to pick some value, let's say this is a, the f of a would be right here. Well, coming in from the left side, coming in from the right side, we also go to that f of a. So the limit value equals the function value at that point. And everywhere along that graph, you would have that condition being satisfied. So we'd say that it's continuous at every point on that graph. And what that definition really implies is that three things must be true for continuity to exist. The limit as x approaches a of f of x has to exist. Can't have that equality if it doesn't exist. So first thing, you got to make sure that limit exists. Second thing, the function value at a has to exist. And then even if both the things exist, there might be a chance they're different, so you have to tie it together and say, yeah, they exist and they're equal. So if anyone ever asks you to show that continuity exists at a point, you got to go through these three steps, basically. You show the limit exists, show the function value exists, and then you verify that they are the same value. So that's continuity, but let's look at some examples here. Let's see what happens when there's discontinuity. And the first one we'll look at here, infinite discontinuity. And that should be discontinuity there. So what happens with this, or when you see this, it's pretty clear you're going to have, something like that where parts of the graph are going up to positive infinity, down to negative infinity. And there's, like that vertical asymptote in between. So you would call this an infinite discontinuity. The next one, jump discontinuity. These are pretty easy to identify as well. You see a jump in the graph from one y value to another y value with a gap in between. You've jumped up or maybe jumped down quickly, and that's just a jump discontinuity. And then last but not least, this graph kind of looks like a 1 over x graph, but really it's some other sort of function where maybe you had a factor in the numerator and denominator that was able to be canceled out. And that factor still led to a domain issue right here, which would be represented by a hole. Remember, with those rational functions, if you cancel a factor out, you don't have a vertical asymptote there, but you will have a hole there. still a domain issue. But what we could do is just define this in a piecewise approach and say, well, f at this x value is just going to be a y value that will fill in that hole. So you've removed the discontinuity. So they'll call this a removable discontinuity when you just see a hole in the graph, because you can just fill in that hole. Okay, so we've looked at the, essentially the two-sided definition, but there is a way to modify the continuity definition by using one-sided limits so we can look at endpoints of a graph. And let's see how that works. In this case, we have a graph that has endpoints on it now. It doesn't go on left and right forever. So what we can do is, let's say, for example, that over here on the left side, this is our A, and we're going to come in from the right. And we would say that if the limit as x approaches A from the positive side coming in from the right of that f of x equals f of A, then it's continuous from the right. Not continuous from the left, because there's nothing over there at that point, at this point here. There's nothing on the left, but we could be continuous from the right. And similarly, if my A was over here now, and we're coming in from the left, we would say, okay, the limit as x goes to A from that left side, that negative side of f of x, if that equals f of A, then we're continuous from the left. So just a way to modify that continuity definition to allow us to work with the endpoints. Just focus on either the left side or the right side and make sure that definition holds with that one-sided limit. All right, so what this leads us to then is this idea of continuity on an interval. So basically, if you have some interval, then it's going to be continuous on the interval if it's continuous at every point within the interval. All the inside points use that two-sided definition of continuity, and then at the endpoints you use the one-sided definition of continuity. And this definition will actually lead to the fact that the following function types are all continuous on their domains. Basically, places where you draw the graph are going to be places where the function is continuous. So let's go ahead and see these function types. Polynomials, things like x cubed plus 5x squared minus 7x, they're going to be continuous on their domains. And really, polynomials, because there are no breaks in the graph at all, ever, they are continuous negative infinity to infinity. Polynomials are always continuous on all real numbers. Rational functions, anywhere we actually draw the rational function graph, that's where it's continuous. Root functions, exponential functions, trigonometric functions, and logarithmic functions all have that same idea where they're continuous on their domains. And basically then, if you want to find where a function of one of those types is continuous, you just need to find the domain. Essentially, as I said, places where you are drawing the actual graph, that's where it's continuous. So let's see an example here of finding where a function is continuous. And if we look at this, f of x equals the natural log of x plus 1, the argument has to be greater than 0. So that means for the domain, we just need to set x plus 1 greater than 0, and we get that x is greater than negative 1. So f of x is continuous then on the interval negative 1 to infinity. The domain interval is where it's continuous. And that's going to really be probably one of the main uses of continuity, or I should say main example of how you're going to use continuity in calculus. You're maybe going to show that it's continuous at a point using that definition, or you're going to show where a function is continuous, and basically because it's continuous on its domain, you just find its domain. All right, so let's take a look at composite functions and continuity. And the thing you have to recall here is what a composite function is. So let's refresh that. So you've got this f of g of x being the composite, and what that really means is that you're going to take the f function and evaluate it at the g of x result. So that's composites. So how do functions that are composites work with limits? Well, continuity does play a role. And it really allows us to kind of focus on the inner part first, in a sense. So we have a theorem that says that if a function f of x is continuous at b and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x is going to equal the f of b. So looking at this form here, you can see that continuity definition coming into play there, where you got a limit equal to a function value. It's just here we are working with that inner function kind of first and putting that into the mix. But we still think about that g of x giving us the b, and that's how it ties it all together. So another way to think about this is that if the limit as x goes to a of f of g of x is just going to be equal to the f of the limit as x goes to a of g of x. So really what they're doing here is they're rewriting this definition up above, where the b is just expressed as the limit as x goes to a of g of x. And the right-hand side there, the last thing I wrote, is what is going to be useful in practice. You're going to be able to focus on the inner function limit and then evaluate the outer function at that limit value. So that's really the big takeaway from this theorem. So for example, let's go ahead and see how this works. And if you want to find the limit as x goes to 2 of x squared plus 5 quantity raised to the negative 2 power, you can think of that x squared plus 5 as being the inner function. So I'm going to find the limit as x goes to 2 of x squared plus 5, and then as long as the outer function, I should say, with that negative 2 power in play is continuous at that inner result, then we can just find that evaluation to get the limit. So let's see what we get here. And x squared plus 5, I can use direct substitution. 2 squared is 4, plus 5 is 9. And we have this 9 to the negative 2 power. So if we thought of the outer function as being like 1 over x to the negative 2, or I should say 1 over x squared. Sorry, x to the negative 2 is 1 over x squared. 1 over x squared is continuous at 9. So we can just evaluate this and get 1 over 81 as our overall limit. So again, focusing on the inner piece allows us to evaluate that separately and then apply the outer function, in this case that negative 2 power, in order to get to the answer. Alright, so intermediate value theorem, last thing we're going to look at here, and probably have to do a second video for this, getting close to time, but basically what the intermediate value theorem says is that if a function is continuous on an interval a to b, closed interval a to b, and there's a value n between f of a and f of b, so this n is going to be some y value between the two function values at the endpoints, and the endpoint function values can't be the same in order for this to all work out, then there must be a number c in that open interval a to b, so some x value in that interval, such that the f of c is equal to n. So what does this look like visually? Well, we're going to have to go over to video part 2 for this one. Run out of time here in my 15-minute allotment, and we'll pick up with the cliffhanger in part 2.